Hello, everybody. I'm Vitek, and it's a pleasure to be here and to be able to tell you about this work. The title of the work is an homage to, doesn't it work? Come on. The title of the work is an homage to a paper by Mitkowitz and Diwan, Sweeney and Hauswirth, called Producing Wrong Data Without Doing Anything Obviously Wrong. And if you haven't read that paper, you should. This is like one of the best papers in computer science. It makes you laugh, it makes you cry. So we'll try to do the same here. All right. And I should say this is work that was done with students and collaborators over a period of about 6 months. So the last few years have been very good for programming languages. There's so many of them that are in use. They're varied, they have interesting features, they're exciting, and each of us have our preferred one, right? We all have our preferences, and if we are given the choice to pick a language for a project, probably most of us would pick different languages. The problem with choosing a language for a large project with many developers is, to paraphrase someone, once you've made that choice, you're kind of stuck with it, right? You have a pile of legacy code, and it's hard to, get back from, that choice. And so the question then is, what is the right language? How do we pick? I work in the programming language community, and unfortunately, we have very little good advice to give you. So what is productivity, programmer productivity? And do various programming languages make you more productive? The answer is, I don't know. I have my preferences, aesthetical choices of mine that will drive me towards one language or another, but, as a community, evaluating programming languages is mostly a failure. It's not even a failure we don't do it. I mean, a failure means we tried and didn't succeed, right? We introduce new languages and new paradigms without a shred of scientific evidence to back those choices. That's typically not considered a good thing. What can we do in our community? Well, there's one thing we know how to do, and that is take an mostly unrepresentative set of benchmark programs and tell you how fast, this language just computes Mandelbrot and whether Mandelbrot is faster in that language or this language. That's what we know how to do. If we wanted to actually measure the productivity of language, we don't have, really much of a clue what to measure, how to measure it. So let's imagine what would be a good experiment. If I wanted to compare, say, C++ and Haskell, I would get teams of programmers, multiple teams with various levels of expertise. I would give them the same task. I would measure all the attributes of the development, and I would repeat that tens of times. And eventually, I would be able to say, well, the projects in Haskell clearly were better because we measured this, this, and that. And I'm not saying you what, because I actually don't know. So this is really a pretty sad state of affairs. And so there are some communities that have tried to answer that question. So the experiment I was describing with large teams that you repeat the same problem is obviously not realistic. So what can we do? Well, if we can't run the right experiment, we may try to see if there's data out there, and maybe from that data we could infer the information we want to get. And one potential source of data is GitHub, right? There's lots of data there. There's, histories of projects written in multiple languages over years by various teams of developers. So can we, from GitHub data, get back to that question of what is a good language? How could we do it? So this talk is about a paper written by this team of researchers from UC Davis at the time. And that paper was called A Large-Scale Study of Programming Languages and Code Quality on GitHub. And the goal of that paper was to answer 4 research questions. I'll focus just on the first one for this talk. The first research question says, are some languages more defect-prone than others? Using a language A, will I get more bugs than using language B? Okay? So that seems to be getting at what we want to know, right? Evaluating languages. So what do they have to work with? Well, they have GitHub, and in GitHub you have this stream of commits that describes changes to code on one or more files written in one or more languages, right? And they have information such as what was the change, who did it, what time, so on and so on. All right. So how did they go about trying to answer this question? They followed the following methodology. So the first thing they did was pick languages. So they used ranking of the most widely used languages. They picked 17. And for those 17 languages, they tried to find the 50 most starred project. So on GitHub, if you like a project, you can give it a star. The more star, probably the more interesting the project in some axis. So they had 800 projects, and they got all of the commits. So that was 1.5 million commits. And each project may be written in multiple languages. So they split the histories according to the languages. So for each project, if there are 2 languages, they'll split that in 2 streams. And then they throw away projects that have too few commits because they're probably not relevant. And then for each commit, they look at the text of the commit and they try to determine, is this commit fixing a bug? If it's fixing a bug, we'll call it a bug-fixing commit. And the idea is that a project that had more bug-fixing commit had more bugs. Yeah. How do they label these? They use, techniques that were written about in software engineering literature, basically looking at keywords and trying to find things that suggest this is a bug fix. Then they apply a negative binomial regression, draw a line across the languages, and if you're above the line, you have more bugs. If you're below the line, you have fewer bugs. So here is the main result from the paper, and the way to read it is you have some control parameters and then your 17 languages, and for each language there's a coefficient, either positive or negative, saying more bugs, fewer bugs, and then there's a p-value that says, is this statistically significant? So anything that is under 0.5 is considered statistically significant. Things that have a dash are not. So to represent this data visually, let's look at the other side of the slide, and you can see that there are 4 languages that I put on top, thinking, because they're better languages, they're closer to heaven, right? And so these are Scala, Haskell, TypeScript, and Clojure. Then there's a bunch of meh languages, that are in the middle, and the color difference represents languages for which the data was not statistically significant. And then there are the bad languages at the bottom. Your PHPs, your Cs, your C++s, and your Objective-Cs. Right? This makes perfect sense, right? This is what we've been telling our students. Well, some of us are been telling us. I see some heads nodding in dissent. But let's say, you know, there is part of the community that would recognize this as, look, statically typed, functional, good, imperative, weakly typed, bad, everything else, meh, right? Okay, so that's what they did. So I read this paper when it was republished, and there was one sentence in the paper that kept bugging at me. So it's like this itch that you have, right? And the sentence said, a single project, Google's V8, a JavaScript project, was responsible for all the errors in the middleware category. So I know that V8 is a virtual machine for running JavaScript, but it is written in C++. So that kept bugging me, and I sort of said, that feels wrong, and if they get that wrong, what else? So eventually we asked the authors to give us their code and their data, and we said, let's have a look. You know, what does the data look like? And in the category of let's have a look, there are several things you can do. So this is the sort of the scale of reproducibility. At the one end, it's you have a paper and results, and what can you believe? Well, you can believe the authors, and that's it. And then you can do what is called a repetition. This is what the artifact evaluation committee does in our conferences. Basically, a repetition is you take the author's code and their data, and you just rerun the thing, and you should get the same results. That sounds very weak, but you know, it's better than nothing. And then you can do a reanalysis where you take their data and code, but you tweak the methods, see how robust the results are. Or you can do a full independent reproduction where you just redo the whole thing from first principles. So the first thing we decided to do was a repetition, because that's easy, right? So we start with a repetition. So we have the data from the authors. It's about 3.4 gigabytes and 700 lines of R code. And I'll just focus on the first research question. So we were mostly able to reproduce the first research question. So this is on the left, there's the original table. On the right is the repetition. You see that arrow points at the fact that when we run their code on their data, we don't get the same result for one of the languages. It's not statistically significant anymore. Or no, the numbers are different. Okay, so that's odd, but you know, that's fine. We'll call this as a successful repetition. We're not able to repeat the other questions for various issues, such as missing code, and data seem to have rotten, but okay. So focusing on the first question. So we said, okay, so we can repeat it. Let's try to reanalyze it, because I was still unsure. So the next step was reanalysis. So what does reanalysis mean? Well, basically, any analysis pipeline looks like this. There is the real world. There is some process to acquire data from the real world. Then you have some process that cleans the data, you know, formats it. Then you have statistical analyses, and then you get a conclusion. So reanalysis simply takes each step and say, well, can we get the same data from the real world? Can we validate that the cleaning process was correct? Can we validate the statistical methods? Do we still get the same conclusion? Simple, right? So that was actually about 5 months of work in the end, right, for 3 people-ish. So what did we find? Well, we found a number of things, and the high-level bit is no, the conclusion doesn't hold. But the interesting thing is why. And For this talk, I'll summarize it in 7 points, which we could think of as 7 sins of data analysis. And I'll just walk you through these points. So, sin 1. So this is from the paper. We have the languages, and there we have the list for each language of the 3 largest projects they had in that language. Okay? Fair enough. So for C, you have Linux, which clocks at 17 million lines of code. Decent sized, real system. For C++, WebKit, or some version of WebKit, clocked at 3 million lines of code. Not bad. There's a Haskell program, Pendoc, that had 20,000 lines of code. Still a real program. Scala had 61,000 lines of code, and then Rails-DevBox had 16 lines of code. Now, the point here is you're going to make conclusions on projects that range from 3 million to 16 lines of code, and somehow they're all treated the same. They have the same weight. It's unlikely to be good. Here's a graph that gives you the same thing in another representation. So this is on one axis the commits in log scale, and the other axis is the number of bugs. And you see I've drawn a line through this, and you can see that most languages are kind of close to that line, but some languages are much fewer commits, and C, for instance, has plenty of them. So you're comparing very, very different beasts, right? So that's first sin. Then I'll just mention this quickly. There's a lot of uncontrolled effects. And like this graph shows, that graph is kind of cute. It shows the lifetime of a project. So these are months. Short lines mean this is a project that is younger. Longer lines means the project has a longer lifetime. And the blue line shows the trend of the proportion of bugs. So if you look at Linux, for instance, the line is flat. It has about the same proportion of bugs per month from one month to the next over the commits. But some projects over time decrease the number of bugs, others increase them. Why? I don't know. But if we aggregate all of this together, it smooshes a lot of effects that certainly, there is information there. As a side note, if you look at Linux, the last few months had way, way fewer bugs. And that looks like a weird outlier, right? Okay. So here's another one. So the same table with the biggest projects. And let me just point out that, so this is WebKit, this is Bitcoin, this is WebKit again, and this is Bitcoin again. So what is going on? Well, we have different variants of the same project that are being included in the study. So we went and we looked at one project to the next, which project had some commits in common. That means they were somehow copied from one another. And we found that the first 17 are variants of Bitcoin, right? So what happened? Well, Bitcoin is highly starred, and people like to replicate it. So very likely, we're double counting bugs. Now, this could be fine or it could be bad, but it's certainly not something you can just ignore. That's only 2% of the data, but maybe that 2% was anomalous. Who knows? So the next bit was a lot of work. So the data we received had the name of projects, but didn't have their owners. And what we wanted to do was validate that the data they got was the real world data. So we wanted to take the project from GitHub and compare the commits that they use with the commits on GitHub. So we started with 729 projects. That was the project they had kept in the study. We found that only 618 projects with the same name were on GitHub, so that means there's like 100 projects that may have been deleted or become private. Out of those 618, we could only match unambiguously 400 of them. That means there were lots of projects with the same name of different owners and we didn't know which one they had used. So we had 400 projects and we found that 100,000 commits were just missing in the data they used. So there was 20% of the real world data wasn't used. And for most languages, so this axis is the percentage of missing commits. For most languages, it's small, but if you go all the way to Perl, 80% of the Perl data was missing, right? So you're saying you have a language and you've thrown away 80% of the commits, and you're comparing that with other languages. Did we throw away commits randomly? We don't know. They're just not there. They should be. Sin 5. So they had data from 2012 going all the back to 2002, I believe. And the first commit for TypeScript was dated 2003. It's okay? Yeah? Any issues with that? Okay. So how is that possible? Right? Time machine? Leaks from Microsoft before the developer had started planning the work. Actually, how did they tell that a file is TypeScript? Well, they told it because it was a .ts extension. What else is a .ts extension? It's a translation file. Translation files are using multilingual software. Usually translation files are not buggy. This is why TypeScript appears all the way at the top of the best languages. Because most of its data was not code. Okay? And, oops, sorry. Let me just go back to this. And the largest project, when we remove the translation file, the largest project that remain are 3 projects that contain only type definitions. So again, no code. So the whole TypeScript data set is useless. So I told you that what got me started was this comment about V8 being tagged as the largest JavaScript project. So indeed, when we looked at their data, V8 is the largest JavaScript project. It has 3,000 commits to JavaScript files, 400 to Python, 7 to C++, and 16 to C. So you say, I mean, this is weird. So we go and we try to understand what these are. It turns out the JavaScript commits are almost all tests. So this was a case of I have a bug in my C++ code and I'm a good programmer, so I'm going to commit a JavaScript repro for that bug. Makes sense. Now, these bugs were all given to JavaScript. Probably they should have been associated with C++. But how come we have so few C++ files? Well, it turns out that extensions, capital C, little cc, capital CPP, C++, CP, CXX, and .h were not included in the study. So no header files for the C code, none of these. The only files that were in C++ were .cpp. So that's about, I think 15% of the C++, I forget, no, 16%. No, that's, I forget how much of the C++ code they actually got, but clearly not all. All right, so here we've gone through the steps of data acquisition, data cleaning, data preparation. So now we're going to the actual problems, statistics. So I told you that they were using Pvalues. Who has used Pvalues before? Yeah, you shouldn't. I'll tell you why. They're bad. But let's assume we like Pvalues. So a p-value is going to tell you something about a hypothesis you're making, if it's statistically significant. Now, we actually don't have a hypothesis. We have 17 hypotheses, because one per language. If we use a single p-value, we will get what is called this Familywise error, and there will be more mistakes. And this is well known. So there's a paper in ICSI where these authors publish, which has said this is one of the most widely committed errors in software engineering literature. So this is not, not a surprise. And there's two ways to correct for this error. One is called Bonferroni, and this is simple. You just divide the p-value, what you get by the number of hypotheses. So you divide it by 16 because I've removed TypeScript, and that's very simple. And the other one is called the false discovery rate. It's a little bit more complex, but there's a citation if you want to use it. It works. And I'll come back to what this means in a bit, but basically fewer languages are now statistically significant. And the last sin that I want to inflict on you is labeling. So this is a study about bugs, right? And the whole point is I have to have a commit that is fixing a bug. So how do I know that a commit is fixing a bug? Well, according to the scheme that the authors used, the first commit here is a bug because there is fault in default. That is what the system returns. The second, which says fix comments, is a bug because we're fixing something. The third one, which says clauses number 153, is not a bug because clause is not a keyword. Interestingly, there's a citation at the bottom from a 2009 paper in the software engineering community that said, don't do this, don't use keywords. And it was written by two of the authors of this study. So what we did is we took 400 of the commits, we took 15 real-world developers, and we asked each developer to label we asked developers to label each commit. So we had 3 developers labeling each commit, and then this allowed us to estimate how far this approach is from the truth. And what we found from that study is that 36% of the bug they called bugs were not bugs, and 11% of things they said were not bugs were actually bugs. But that's a big difference, right? So now suddenly you're working with data that is fuzzy, right? You can't trust those numbers you're getting for each project, because any project may be off in some way, depending just how people write their commit messages. So, to sum up, so all the way here is, on the left is the original data. All the way on the right is the result of using Bootstrap, where basically we're sort of simulating what could be possible. We assume there's a 36% false positive, and we simulate data that would be, hey, if we were 36% of the time we're wrong, what would we get? And what I'm going to show you is out of the 13, so they had 17 languages originally, 13 were statistically significant. What is left once we do all of the steps that I've described? So C isn't statistically significant anymore. Objective-C isn't statistically significant anymore. JavaScript isn't anymore. TypeScript, we've just got rid of it because there wasn't anything there. PHP is not statistically significant. Python isn't statistically significant. Scala isn't statistically significant. Perl, 80% is missing, so even if it is statistically significant, we'll just remove it. And then in yellow, I have all the languages that were already not statistically significant. So, we're left with 4. Does that still paint a picture that has anything to say? Well, the worst language is C++. All right, fine, let's say. And the best language is Clojure, followed by Haskell, and followed by Ruby. Ruby? Okay, perhaps, maybe. Odd. So, at the beginning, at the outset, I've told you that p-values should not be used. Well, they shouldn't. I'm not a statistician. I married one, so I have, this is just, sort of knowledge that I acquired on the way. But the statistical community, and I have some references here on this slide, have recognized that p-values are not useful, and especially when you have large data. So as your data grows, it's much and much easier to have statistically significant p-values. So p-values are unusable, and if you have doing large scale anything, definitely meaningless. So what can you do? Well, you can try to estimate the practical significance of what you've observed. And here this graph maps a simulation where we take the error rate of the two languages, the one that has the worst behavior and the best, C++ and Clojure. And what the graph shows is the predicted bugs for a particular number of commits. And what you'll see in this graph is that both of these languages mostly overlap. So you couldn't tell if I just gave you a number of commit and a number of bug, you couldn't tell if this is a language written in C++ or Clojure. There's nothing here, right? There's no information. All right. So, back to our paper. So this is the FSC 2014 paper that we've been talking about. And this was well received. It was well received enough that it was chosen as a research highlight and published after a second round of reviews in CACM. Okay? And that was in 2017. And then, the conversation starts. So you have your social media, and they're saying this, and they're saying the shocking secret about static types, and they're saying less code, less bugs with functional programming. They're saying statically typed functional languages win, and they are saying boom. I don't have anything against all those people. They may be right. What I have, my problem is that what was presented was at best an association, right? And the interesting thing is the authors were careful. In the statement of their results, they wrote, some languages have a greater association with defects than others, although the effect is small, right? So they were careful. Yet everybody who read this paper jumped to the conclusion that, this causes that. And this is, I think, maybe one of the biggest messages of this talk, is as scientists, when we write stuff, we should be careful to not lead people to those conclusions, and as readers, we should be careful not to jump to them. So we did last thing, we did a citation analysis. So what we did was we took 120 papers that cited the original work, both from other authors and the authors of the paper, and we counted. So 77 of them had just cursory references to the work. So this is the kind of citation when you have 10 citations in a row, and this was one of them. Okay? Then 12 paper talked about methods. So they said, oh, the FSC paper used that kind of GitHub analysis and so on. Then 2 paper cited the results of the study, but used association, correlation language. They said, yes, they found an association. And 24 of them used causal language. And also 3 papers by the authors, who had been careful when they wrote the original work to say the right things, but then got maybe carried out, sort of enthusiasm took over. All right, so we're almost done. So we did this, and We decided to write it up because, you know, that was some amount of work. And we put the thing on archive last year. And, well, there were positive comments from friends. In England, we were called boffins, which I had to check whether it was an insult or a positive.
What's the answer?
It's positive, scientists. I'm a boffin now. So that was good, but we also tried to submit it to conferences, right? Because we want, you know, the community to know. So what happened? Well, we submitted to FSE, where they had the original paper, and the rejections were for what reasons? I think I have them. Oh, the first one is, why do you use Bonferroni and not FDR? Okay, so we used, in the revision, we used both and it doesn't make a difference. Then, your paper doesn't have code and data attached to it. Well, it was double blind. We were not supposed to attach, but fine, okay. So of course, we have code and data. And then what was the third thing they didn't like? Oh, this is a multi-line. So they said the bootstrapping method is clever, but it relies on limited bug labeling data. And they suggested we have more people rate the commits, which we did in the revision. We took 15 real-world developers. So, you know, they are not horrible comments by any means. I mean, all of this is true. Yeah, we're a bit disappointed because if somebody came to my work and said, hey, you're an idiot, you published crap, I would say, okay, tell me how, and I'll try to fix it. So then we tried ICSI. This is the other conference in that community. And there, what did we get? The reanalysis actually confirmed the original conclusion. Okay. I guess we had numbers, they had numbers. Essentially the same results, given some differences in operationalization. Okay. You know, given the fact they were wrong, yeah, they were fine. And the last one is, this paper appears politically motivated. I'm such an apolitical guy, I wouldn't be controversial. Why, did they think that? I don't know. So, the status of our work is it got accepted to Toplas, which is nice. So it will at least appear. I don't think many people in the software engineering community will read it. And I'm guaranteeing you that the number of citations will be one order of magnitude than the original, less than the original. But at least it's out there. The truth is out there. So, voila. And, there's an artifact. You can redo anything we did. The paper is fully reproducible. Thank you very much.
Did you at least get a thank you from the original authors?
So the question is, did I hear from the original authors? Sorry?
Yes, did you hear?
Yeah. So when the paper appeared on Archive, they contacted us and they complained about one thing in that article because Emery said that, had a joke about if you torture data enough, it will confess. And they said you have to retract that from the register article. And we weren't, like, why? And they said then, okay, then we will talk to you once your paper is accepted at a peer-reviewed publication. Right. Yeah, there's a...
Right. First of all, thanks, of course, and second, that this is a large-scale research. It's kind of scary that it's so flawless, flawful. But I was wondering about the definition of the bug here was that it was annotated in some way. You did it a bit of a different way, but it only proves how often bugs got fixed, but not really how often bugs appear at languages. So maybe if you just, do some math on the issues created and how quickly they get fixed, you get something.
I know where you're going. So there's two things you said. The first thing you said is it's based on large data, it's scary. I guess that it's wrong. But I would claim that the more data, the more likely you get bad answers. Because like all of these mistakes took us time to find out. We had really to understand the data to scratch. And so I would submit that I trust large-scale studies much less than small ones. The second thing is, all of this that I described are small details. The fundamental here is I don't think that with raw GitHub data, you will ever get that answer. There's so much more going on. Like a project that has many customers will have more bug reports and therefore more bug fixes. There's so many things, the team, it's just not possible to answer that. But if we had written a letter saying, hey, this is not possible, you know, your paper can't answer that, nobody would have paid attention. If we can show the paper is wrong on their grounds, using their metrics, then you know, in the discussion section, we can write, oh, and by the way, there's many more reasons why you shouldn't do this.
Right, so I have two questions. Question number one is, given that it's, as you know, as soon as a paper is published, it's pretty hard to refute it, so to speak, you know, do you think it should be, you know, the reviewing process and everything should make it easier to, you know, refute an already published paper? So this is question number one. And question number two is, you said that, you know, even as a scientist, you have to write stuff carefully so that people don't jump to conclusions. Problem is, people will jump to conclusions anyway. So what do you think should be done in, you know, such a case to, you know, prevent people from actually jumping to conclusions?
So your first question, so let me take in reverse order. So how to prevent people from jumping to conclusion? I don't know. You guys voted for Brexit. We voted for Trump. Obviously,
first of all,
you know, the population will make some amount of mistake from time to time. There's nothing we can do. All we can do is, as scientists, is write things clearly and avoid clickbait, right? So, and what was the first question?
Well, the first question was, given that it's hard to, you know, you see a paper that's already published.
Yes, the reviewing aspect, yeah. So the reviewing aspect, so there's no way, I mean, I don't fault the FSC reviewers for missing all of the things I showed you, because they're hidden in the data, in the math. They're not in the paper, right? So there's no way the reviewers could have caught them. What they could have caught is, like this, even if you do this, you're not going to get the answer, but it's hard to argue. So I think, no, this paper should have been accepted. Where our community fails is we don't value reproduction studies, because, you know, normally the scientific standard is somebody say, you know, the moon is made out of cheese. Okay, maybe, I mean, from afar, could be. And then somebody else says, I can confirm that, I did the equation, you know, or says, no, this is nonsense. That's the normal way, right? Reviewers, they have so little time, such a small window to judge, they're mostly saying, is it plausible? You know, is it plausible and is it interesting? And that's the other problem is reviewers tend to look at shiny things, right? So if you're very careful about your claims, if that paper had been very careful about its claim, it would probably not have been published, right? So they want something that sounds noteworthy. If we just say, oh, you know, sometimes I have more bugs with some languages, but really we can't conclude anything, I would never have passed, right? Yeah.
So this is lovely. I'm glad very happy you did this, but I do have some objections. First of all, I object to your last statement that this paper should have been accepted.
I said it should have been.
Should. I object to that.
Okay.
I think that this would be a wrong conclusion. So you're saying there is a way to even do this right?
No.
With
sorry.
800 applications and 17 languages?
Yeah, okay, yeah.
I think that paper should have been rejected on premise. Anything that tries to draw these overgeneral conclusions when there are such evident biases to begin with. I think as a community we should be favoring very clear small questions. If you were to tell me I will do an experiment that would be Haskell versus C++ with a lot of experiment subjects, then I might start paying attention. It's a very clear question, at least. But I don't, so I will not agree that this paper in principle should have been accepted, but I do agree that the way our reviewing processes work is such that this looks like a great paper.
Yeah. So I agree with you on the fundamentals. What I meant was all of the mistakes we found, I don't think reviewers could have found by reading the paper. Right? So like the more, fundamental part of is this idea, this research, this set of research questions and the methodology even sound? Yeah, I agree with you. This is not sound. I don't think they can ever get the right answer. But the mistakes I'm mentioning, you couldn't have seen without doing the work we did.
So do you think that one can do this right? Do you think
that particular study?
No,
or this direction?
Yes. Can someone do a statistical study and answer the question of whether some languages are more error-prone than others? Do you think there is a way to do it right? I'm not saying if you did it, you found there was no correlation. That just says inconclusive.
Do you think
someone could say there's definitely no relationship, or there is some relationship?
So I think there are so many confounders that you have to untangle all of these issues. Honestly, I don't know. I mean, I tend to think no, but yeah.
I would also tend to think no, just because of pre-existing biases, like how one chooses a language to begin with.
There's one and two. Yep. Phil? And there's one here. Yep.
So it's very clear that it'd be very good if we could imply empirical techniques to resolve some of these questions. Right? I jump up and down and say functional languages are great, but in terms of empirical evidence of the kind that scientists accept, there's very little on the ground. Mm-hmm. So the fact that they did this study at all, I think, is very much to be applauded. And I'm slightly worried, right? Any study of this kind. Sorry?
What's to be applauded? You applaud something that's very, very difficult. Who had not thought of doing this study before? I don't know of anyone in this room who hasn't had that thought cross their mind in the past. What's this to be applauded?
It hadn't occurred to me to look at GitHub data to get this out.
So you had two points, and there's another question here.
But I just wanted to say, right, anytime somebody does this, of course, it's always very easy to attack any study of this kind. So I'm slightly worried that after you've done this, that the next person that thinks of doing it will put their head down and say, oh no, I better not do it because Emery and Jan will attack me.
Yeah, but this was careless. I'm sorry. I mean, some of this was really sloppy. It's a good question, but there were mistakes that are really glaring when you actually look at the data. I have sympathy for the authors, but it's wrong. What can we do? I can't applaud that. And what I do mind is that people keep citing this, right? Just because it goes along with our common accepted wisdom. And now it's a thing you can say, oh, these languages are bad because, FSC 2014. And I mind that, because that's not supported by the data. It may be true, but it's not supported by the data. Don't put a cite there. Say, I believe. That's fine. I believe lots of things. And I think we should be allowed to express beliefs. There's a question here.
I just wanted to refine a question you were just asked. You said that you don't know of a way to do it right, but what if the effect were very large? So suppose that the difference between C++ and Haskell is 10 times more bugs.
Yeah.
Would that be easy then? And does that mean that if you've not found anything, is that any sort of evidence against the effect being very large?
I think we just can't tell. The data is just so confusing, and there's so much noise that there may be a large effect. Because, so the majority of bugs are bugs of the kind, hey, the TCP/IP port is wrong. Unless you have a very powerful type system with dependent types, you're probably not going to catch that, right? That is not specific to the language. So 36% of the bug are mislabeled. Amongst the remaining, a lot of them are not relevant to the question you're really asking. So how much signal is there? Yeah.
Just as a comment, I think there is something political here, clearly. It's the PL community versus the SC community. Very much so. And I think, I'm not sure if everyone in the room knows that SC is winning very convincingly. They move fast and break things, and they don't care about what they publish and how true it is. And as a community, it grows a lot. It's much easier to enter. ICSI had 1,800 attendees this year. No refutation of any visible SC results has made the slightest difference in the careers of people involved in them. I can name numerous examples, including the first author of the study you're debunking. So, they're doing fine, right? And we are just jealous.
Yep.
Let's be cynical here.
Yeah,
the most mediocre senior software engineering researcher has more citations than you or me. Or Phil, for that matter. I mean, maybe you need to go a little higher in how senior they are. But really, they're a large community, and they publish lots of stuff.
Yeah.
And hey, they're winning.
Yeah, I will not say more than I'm happy to be the grumpy old man in that story. On my backyard. All right, thank you very much.